Hi there! This is Teacher Geraldine and today we are going to discuss Isaac Newton's third law of motion. You probably know that when you walk or run or jog like them, you are actually exerting force on the ground by stepping on it. But what you didn't realize, the ground is also exerting force by pushing you upward. Amazing, right? This fact is the consequence of Newton's third law of motion, the law of interaction, and this will be the focus of our discussion. And by the way, who is Isaac Newton and his laws of motion? Well, let's try to go back to our previous lesson. Isaac Newton was an English mathematician and physicist who discovered the laws of motion. The first law of motion is known as the law of inertia. It states that an object at rest remains at rest. An object in motion remains in motion unless acted upon by an external unbalanced force. Also, it states that different objects have different amounts of inertia, the tendency of an object to resist a change in position. And the inertia of an object depends on its mass. Thus, the heavier the object, the greater the force is needed to change its position or motion. Further, the change in an object's motion or velocity over a period of time is referred to as acceleration. Therefore, the greater the force applied to an object, the greater the acceleration. A net force is produced when two interacting objects produce an unbalanced force, and the direction of the object's acceleration follows the direction of the net force. This gives us the concept of the second law of motion, the law of acceleration, which states that acceleration is directly proportional to the force, but inversely proportional to the mass of the object. This can be expressed in this equation. Acceleration is equal to force over mass. The third law of motion is known as the law of interaction. It states that for every action, there is an equal and opposite reaction. Take note, equal in size, opposite in direction. Thus, if object A exerts a force on object B, then object B must exert a force of equal magnitude and opposite direction back on object A. Moreover, forces always come in pairs. This pair is known as action-reaction force pair. Identifying and describing action-reaction force pair is just a matter of identifying the two interacting objects and making statements describing who is pushing on whom and in what direction. To understand it more, Patrolwoman Masumbol of GSCPO CMFC will demonstrate to us how the gun fires. Let's play it again, this time in a slow motion. Observe that when a bullet is fired from the gun exerts a force on the bullet in forward direction. This is what we call an action force. The bullet also exerts an equal force on the gun in backward direction. The backward movement of the gun is called the recoil of the gun, and the recoil of the gun is the reaction force. Interesting, right? Another illustration is the deflating of balloon. When the air goes out from balloon, it pushes the balloon in the opposite direction. Observe that the balloon moves forward as the air moves backward, an explicit example of the action-reaction forces, isn't it? Now let's identify the action-reaction force here. Take note, the action force here is the one who or which is pushing. In this case, it is the balloon which pushes the air out. How about the reaction force? The one that reacts to the push is the reaction force. In this case, it would be the air that pushes the balloon forward. Now let's try to identify the pair of action-reaction forces in the next illustration. What is the action force? How about the reaction force? I will give you 10 seconds to identify the pair of action-reaction forces. Very good! You got it! The action force is the dribbling of the ball where the ball is pushed downward. And the reaction force is the bouncing of the ball where the ball moves upward. Try another one. The wheel on the tricycle as it travels along the street. I will give you another 10 seconds to identify the pair of action-reaction forces. Good job! You're so smart! The action force is the wheel pushing the ground backward, while the reaction force is the ground pushing the wheel forward, making the tricycle move to the direction of the net force. How about this one? A man skating. What do you think would be the action and reaction force? I will give you another 10 seconds to identify the pair of action-reaction forces. Brilliant! You're really a smart kid. The action force here is the skater pushing the ground backward, while the action force is the ground pushing the skater to move forward. But why do the skater move if the magnitude is equal? This is actually the common misconception on the action-reaction forces. The idea of equal magnitude may seem to be confusing because it seems to imply that forces are balanced so the object will not move. Let it be cleared that this idea is incorrect. Even though the forces are equal in magnitude and opposite in direction, they do not cancel each other because action-reaction forces act on different objects. Action-reaction forces is only confined in an isolated system, and this system refers to the pair of action-reaction forces. You must understand that the concept of action-reaction forces lies within an isolated system, meaning the pair of forces is not affected by any pairs of force observed in a given situation. Notice that there are more than two systems or pair of action-reaction forces that can be identified in this illustration. But let us just consider isolating two systems here. Okay, let us try to identify at least two pairs of action-reaction forces or two systems in the given illustration. Have you seen it? As you can see, there are more than two systems or pairs of action-reaction forces that can be identified in the given illustration. But let us just consider these two systems. For system A, we have the gravity pulling the skater downward for our action force, and we also have the ground pushing the skater upward for our reaction force. And for system B, our action force here is the skater pushes the ground backward, while the reaction force is the ground pushes the skater to move forward. In learning to isolate system or pair of action-reaction forces, you will be able to understand that forces in a system do not cancel each other because they are not affected by the forces of the other system in a given situation. But why does the skater move? It is because a net force is acting on these systems. It may mean that system B has greater force than that of system A. Thus, the direction of the object will follow the direction of the net force. Now, let's sum up what you have learned. I will be giving concepts regarding the action-reaction forces. Say action if the concept is correct and reaction if the concept is incorrect. Let's try. The correct answer is action! Now it's your turn. Good job! The correct answer is action! Good job! The correct answer is action! You got it! The correct answer is reaction! Way to go! The correct answer is reaction! You are so smart. You got it. The correct answer is action. This time, I will be asking you to help me explain to the little boy in the picture how to move the boat forward. What do you think will move the boat forward? I will be giving you tip. Use the concept of action-reaction forces. Think, think, think! You got it! You're so smart! The boy needs to paddle backward so the water will push the boat forward. I am happy that you have learned the concept of the law of interaction. Can you state it once again? Very good! The law of interaction states that in every action, there is an equal but opposite reaction. Don't forget, have fun learning! Bye-bye!